chapter 9 dealt with all the gas cycles where we got to assume ideal gas. Chapter 10, we do not get to assume ideal gas, okay? Because we're changing phase and there's a lot of energy in latent heat. Okay? All right, so first off, okay, we have a phase change that we're going to try to utilize. So how best can we utilize it? Well, you can start with trying to create a Carnot vapor cycle. So throwing the Carnot cycle onto a vapor dome. Well, if we do that, we have these two diagrams that we kind of throwing the Carnot on there. On the right in A, we have 1 to 2, which we can do. We could do that. If have a constant pressure process, go from saturated liquid to saturated vapor. But what it does is it limits our temperature. So if we're using water, this max temperature is right here. Right? That's the maximum temperature we could have, which limits our Carnot efficiency. Since the Carnot is the reversible, which is 1 minus TL over TH, that point limits TH. That's the max kind of TH we could have, okay, with water as our fluid. Then we have these other, we have the turbine that we're going to use in a vapor cycle, so we would expand isentropically from 3. But in this case, now we have a quality to the fluid, so that means that there's liquid and vapor. And a turbine does not like the liquid droplets. There's erosion that occurs, okay? So we want to stay somewhere really close to the dome or in the vapor section the whole time. Okay, so we want to really stay over here, okay? Same with if we're compressing, okay? We're raising the pressure on the left. Here we would have a two-phase fluid of mostly liquid and a little bit of vapor, and a compressor doesn't like that. Compressor likes vapor, right? A pump likes liquid, so a pump could be out here, okay? So if we then instead push this Carnot cycle up in this part B equation, we have 3 to 4 constant pressure heat rejection we can do. Now we're in this vapor phase for the turbine that we can expand as all a vapor, which we can do. The turbine likes that. Here we can use a pump and raise that pressure, so that's good. So there's a smiley face there. There's a smiley face, right? We got a smiley face. But on this 1 to 2, it's a isothermal heat addition process that's occurring, trying to occur it in a boiler, but the pressure is changing if you're using water throughout that. You're not changing phase anymore. That keeps the pressure the same. You're going through a whole bunch of pressures as you're trying to go from 1 to 2, and that's really not a very practical process with this variable pressures here, okay, at extremely high pressure. So this one is a frowny face, right? Just like we had frowny face over here and frowny face on this side. This one was kind of meh face, so we'll just leave it like that because we could do it, but we limit our TH, right? So what do we do instead? We have the Rankine cycle, okay? And it allows that practicality in there. So we've now have the turbine operate mostly in that vapor section. So there's just a little bit of water in that state 4, okay? Moves all the way to the left. So 1 to 2 is using a pump to raise the pressure, okay? So then it's all liquid. We can use a pump and we're not going to have any issues with erosion on compressor blades, okay? And then we have constant pressure heat addition, so we're just following our constant pressure line from 2 to 3, and then following our constant pressure line from 4 to 1, okay? So all these things we can do with devices, okay? So we have our isentropic compression, constant pressure heat addition, isentropic expansion, constant pressure heat rejection, okay? So it is similar to the Brayton cycle, but we're dealing with the phase change, so they call things different, right? Because we have turbines still to expand and get work out. We have a heat exchanger to reject heat, but it's called a condenser because we're changing the fluid from a kind of a vapor to a liquid. So we're condensing it. Just like the boiler, it's a heat exchanger. We're calling it a boiler because we're changing from a compressed liquid at state 2 all the way to a superheated vapor. Okay, and then we have our pump. Right, we had a compressor in the Brayton cycle because we were dealing with all gas, but now we have liquid at 1 to 2, so we have a pump. Pump raises the pressure of a liquid. Compressor raises the pressure of a gas. All right, so then we apply the conservation of energy, right? And we utilize that steady flow. So that steady flow is where we have dE dt equal to 0. And then we're neglecting kinetic energy and potential energy, right? And that's where we had that Q minus W equals delta H that we use in the example we just did, okay? Well, we can use that still for the Rankine cycle because it's just one inlet, one outlet on each of those devices, the pump, boiler, turbine, condenser, okay? So on the pump, then we just have delta H. On the boiler, we have delta H for the boiler, turbine, delta H, condenser, delta H. The only additional thing we have for the pump is we have this, okay? We have the reversible steady flow equation where work is equal to the integral of V dP when it's steady flow work. So we had in a piston cylinder device, we have the reversible was P delta V, but in a steady flowing device, the reversible work is V dP. While for a pump from 1 to 2, we can actually take specific volume out of the integral by assuming it's incompressible. And we just have V delta P. So we'll utilize this equation a lot for the pump. Okay. The other thing is for pumps, we're going to have the assumption right here that goes with the Rankine cycle that state 1 right here has a quality of 0. So, and any inlets to pumps, any additional pumps would have a quality of 0 because a pump needs it to be a liquid. Okay. All right, so then we use our work net, which is turbine work minus the pump work. So work out minus work in, which is Q in minus Q out, which we just looked at. Thermal efficiency, same equation, okay? So work net over Q in, or when we put in Q in minus Q out, we can simplify it to that, okay? Power plants often use this heat rate, which just takes the thermal efficiency and rearranges it for this term heat rate, which just talks about the BTUs of heat supply per kilowatt hour of electricity. All right, deviation from actual cycles, because the Rankine cycle is an idealized one, okay? So we're going to have friction and heat loss to the surroundings from irreversibilities. So we have in the pump irreversibilities and the turbine irreversibilities. We have pressure loss you see from 1 to 2 in the boiler and pressure drop in the condenser. While we can, with the isentropic efficiencies, just like we did for chapter 9, but we got to stay in enthalpy because we can't use Cp delta T for water. We can use the isentropic efficiencies for the pump and the turbine to better analyze the cycle and get a better answer. Great. All right, so then how can we improve this basic Rankine cycle and increase its efficiency? Well, the main thing is going back to the reversible Carnot efficiency, 1 minus TL over TH. We can use that to kind of understand how we can increase the actual size one, okay? Well, in this, we see we want TL to be low and TH to be high, right? That would increase the Carnot's efficiency. So we can apply that to the actual cycle, okay? Here, by low the condenser's pressure, so we go from 4 to 4 prime, that means we lowered the condenser's pressure and we just created this area right here and increases the work and increases the efficiency. Okay. There's a limit on how far we can go down because it still has to be cooled by cooling water or air. So we still have a limit there, but most condensers in a steam power plant operate under vacuum pressure. So pressure is lower than 100 kPa to get that additional work there. Okay. So the added effect from 4 to 4 prime is we just increased the moisture content. So we lowered the quality. Right now we're going to have, maybe 90% in that case of our quality instead of 100%. Okay, so we got to worry about moisture content or do something else to lower that. Okay. Another thing we can do is superheat the water before the turbine. So just heat it up to 3 prime. So instead of 3, go up to 3 prime. So superheat that and raise TH. Okay, so kind of raising that average temperature that we're adding heat. So that goes from 3 to 3 prime. Okay, so that'll give us this work, and it would also put that 4 prime closer to being a quality of 1. We do have a max that we can go here. Okay, the book has about 620 degrees Celsius. Okay, as our max from material considerations. Okay, and that first stage, the early stage of the turbine, is going to get hit with all this high temperature. Okay, so if we have this limit of TH being, we have this T max that we can achieve, and that's the max that we can get to, well then we can also increase the boiler pressure, right? So if we increase the boiler pressure, we're going to go from 2 to 2 prime because we're going to increase the pressure on the pump to raise the pressure higher. That gets us to this 3 prime because we have a max temperature we can achieve, right? So we raised it all the way to get to 3 prime. But if we expand it through a turbine, we're going to have that high moisture content again. But what we do instead is we reheat right here. Okay, so we can stop the expansion to the turbine right there, reheat to 3, and then expand again through another turbine. And that gets us back to a nicer quality at the exit of the turbine. And all this raises the TH average that we're adding when we're adding heat in, the average temperature. So here is the ideal reheat cycle then, what was just shown. Okay, all we're doing is start at 1, have our pump that isentropically, we raise the pressure and temperature. Then we have our boiler. So now we're adding heat at constant pressure. So we add heat, we get to state 3. Then we expand to the turbine. So we expand, and we stop here at 4. Okay, and we reheat it. So we add additional heat back in at constant pressure to get us back up. And now we're at 5, and we expand through the turbine, this low pressure turbine, all the way to the condenser's pressure. And now the quality here is a more reasonable quality that the turbine can deal with instead of if we expand it all the way right here with 1 turbine. Okay. And then we have our condenser back to 1. So we get all this area for our work. Okay, so that means we have change in enthalpy in the initial boiler, what's called the primary, and then the reheat. Turbine, we have 2 workouts, right? We have 3 to 4, 5 to 1. We still have a work in for the pump though too, right? So that's the work out. So then work net is these works minus the work of the pump, or Q in minus Q out.
So by having it a low pressure turbine allows heat out like easier, or
heat out. It's more about this turbine blades here. So the later stages of the turbine blades, by having that second turbine, by that reheat and going over here, we would normally be here, and it's not dealing with this part, it's dealing with this part that the turbine can't handle as well, okay, because of erosion on the blades. So now that you'd have lots of water droplets, right? And it becomes, basically erodes those blades very quickly if you've got these droplets on the turbine blades, okay? They can handle a little tiny bit, which you see over here, but not as much as if you went from 3 all the way down. So we reheat it and then expand. Okay. The Q out, we can take the Q out either way. Right? It does increase it right here, but we also get more work here. All right, so if we just kept reheating and expanding, reheating, expanding, we would end up getting kind of like this what's being shown here, almost like an isothermal. But there's kind of a limit there. So with a single reheat, you get about a 4 to 5% efficiency improvement, but that drops as you add more and more. Okay, so really, from practicality, it's like 2 reheat stages. Beyond that, it becomes not very practical. Lots of extra device and expense for not as much improvement. All right, the last kind of modification is the regenerative cycle. So this is with a regenerator. Okay, so we talked about a regenerator, borrowing energy from one part of the cycle and putting it into another, like in the Braden cycle. We did that. We talked about that. In the Rankine cycle, these are called feed water heaters. So they call them feed water heaters instead because it's more specific to these Rankine of what they're doing, but they're a type of regenerator. Okay, and what it's doing is moving thermal energy from over here somewhere, right, and putting it over here so that this, where we would normally add heat from 2 all the way to 3, we're going to try to use the regenerators to get us to as close as we can to 2 prime. So then the TH, that kind of average TH, is just from 2 prime to 3, right? Without a regenerator, that average TH is from 2 to 3. So that's all the way from here all the way up. So this one would be lower, and this is higher. So that means this is going to have a higher thermal efficiency because we're increasing the temperature, the average temperature, which we're adding heat. Okay. We have 2 different feed water heaters. So there's an open feed water heater and a closed. Okay, and we'll go through those. Open is basically like a mixing chamber. You're directly exchanging the thermal energy by mixing the fluids together. Closed feed water heater is a heat exchanger where you're in separate pipes, not actually contacting each other. Okay. So here's open feed water heater. Okay, it's just a mixing chamber right here. Okay, we're taking 6 and mixing it with 2 to give us 3. Okay. We will kind of walk through the cycle. Okay, so we start at 1, which again, it's the inlet to a pump, so it's a quality of 0 right there. Isentropically compress it through the pump to the feed water heater's pressure. Okay. While the feed water heater, it's open feed water heater, so the fluids are all open and mixing, so that means the pressures at 6, 2, and 1 all have to be the same. There's nothing modifying the pressures. So 2, 3, and 6 are all on that same pressure line. Okay. And 6 is mixing with 2 to give us 3, right? 3 is that inlet to the pump, so we're quality of 0. So 2 is going to 3, and 6 is going to 2 because they're mixing together. Okay. Now we go through another pump right here. So we add pressure isentropically up to this highest pressure. And now we go through our boiler where we're adding heat. Okay, so we go from left to right, all the way to the superheated. And now we go through our turbine. So if we expanded all the way through the turbine to the condenser pressure, we would go from 5 all the way to 7. So, but what's happening is a fraction of that steam or that water is being pulled at a mid pressure here at 6 for that open feed water heater. Okay. And then the condenser again is 7 to 1 right here. So all we're adding heat externally is from 4 to 1 in this feed water heater system. All right, so conservation of energy equations are shown above, and there's a little bit of a difference here, right? Heat in, it's just delta H. Heat out, we have this 1 minus Y here, and we see it in the turbine, we see it in this pump 1, and this Y is this fraction of steam extracted, mass flow rate 6 over 5, okay? So what does that mean, and why does that come from? Because the mass flow rate is not the same throughout the whole cycle, okay? We see all of the masses here through the boiler, 5, it could split in the turbine, and then it comes back together in the open feed water heater, and we get their full mass again through pump 2. Okay, so what that means is if we do the conservation of mass on the turbine, we would have mass flow rate 5 minus 6 minus 7 is equal to 0, right? So we have one inlet of 6, we have the outlet, or one inlet of 5, the outlet is 6 and 7, okay? Well, if we divide that mass flow rate each term by 5, which is the total, the max mass flow rate that we have through the boiler, we're going to get, that'll be 1. It's mass flow rate 5 divided by 5, so we have 1. 6 divided by 5, 6 divided by 5 is what we have defined right here, okay? So that's Y. We have 1 minus Y, because this is Y. And then that will end up being equal to mass flow rate 7 divided by mass flow rate 5, okay? Is 1 minus Y. So that means Y is going through here. 1 minus Y is going through here if we divide it by mass flow rate 5. So what's happening is we're dividing every conservation of energy by that mass flow rate 5, that maximum mass flow rate. And that's where you get these 1 minus Y's from, okay? Because if we do heat out, this would be mass flow rate 7. You divide it by mass flow rate 5. That means then it's 1 minus Y here, okay? And the whole reason you do this is for your thermal efficiency. Because work net in rate form over heat in rate form is this. When we divide it to make it lowercase, we're dividing each of them by the same mass rate. So to make work net, to make it divide both by the mass flow rate 5, let's say, we would have work net divided by mass flow rate 5, which is lowercase work, Q in divided by mass flow rate 5, which is lowercase Q in, but they're lowercase from mass flow rate 5, not from, for the turbine, let's say, it's not from mass flow rate 7, it's from when we divide it by mass flow rate 5 on both the numerator and the denominator, it's the same mass flow rate, so we got to divide everything by mass flow rate 5, and that's why these come into play. Okay. And we'll do an example on that in class. The closed feed water heater, the difference in this one is now the fluids aren't touching directly, so they're at different pressures. So 7 is flowing to 3 and just exchanging heat with 2 to 9, but the pressures aren't the same. For the open feed water, they were the same pressures because it was all open, all mixing. Okay, So if we work our way through this one, we have our inlets to our pumps. So 3 and 1 are at quality of 0. Okay. Let me erase that circle. I'm going to need that. All right. So then we go pump and we raise with this pump all the way up. We actually raise it all the way up to the highest pressure because we are here. There's a mixing chamber right here, which means this is all at the same pressure in the mixing chambers because they're all connected and mixing. And this is the same pressure. So it's 2 is all the way on the max pressure. All right, now we have 7 and 3 heating up 2 to 9. So we get all the way up to 9 here, that same temperature that 3 is at, because that's the max we could get to our temperature at 9. Now we go through a mixing chamber. So 9 and 4 mix together to give us 5. So 5 is going to be a point in between 9 and 4. Okay, so we'll come back around and show the other loop in a second. So we mix 9 and 4, and that gives us 5, right? And now we add heat in the boiler from 5, and that takes us all the way to 6. Okay, we expand all the way through the turbine. That'll get us to the condenser pressure and temperature, and then we have our rejection of heat here. Okay, at 8. While 7, we pull some at an intermediate pressure to go, and that gets pulled all the way to this pump to preheat the other side. Okay, and then we're at 3. We have to get into this mixing chamber. We have to raise the pressure of that fluid. Otherwise, it's not going to be at that high pressure anymore. We're going to drop pressure, and then they'd be all mixing at a lower pressure. To get it to that same high pressure, we got to raise the pressure of 3 up to that same pressure in the mixing chamber. Raise its pressure up to 4, and now it can be combined with 9, give us 5. Okay. All right, here is more what a actual power plant looks like. So we have closed feed water heaters, an open one, another closed. So they have all these combination of devices, and they have these traps. It's being shown instead because they're taking out of the closed feed water heater and putting it down to a lower pressure in this one. So they're basically dropping pressure with this to put it down to there and dropping pressure again to there. Okay. Just to make it more complex, what's going on a lot now to increase efficiency is this combined gas steam power plant. Because gas turbines get higher temperatures because we can keep the cooling down of what the blades will experience. So we would have basically a Brayton cycle right here, okay? And then you have a Rankine cycle. So you have chapter 9 and chapter 10 going on here. So you have the Brayton cycle, and then the heat that would normally get rejected to the atmosphere in the Brayton cycle is used for the heat in on the Rankine cycle. So then you only get heat in right here externally, heat out of this condenser here, and then heat out right there. Okay, so there's just this heat in and those 2 heat outs. So you're actually going to get a higher efficiency with this, and you can get over 50% efficiency with these combined gas vapor power cycles. Okay. And then the second law analysis on the cycles, these equations are the same as the last chapter. The only difference is the closed system versions are on because all of chapter 10 deals with open system components, where we had the Otto and the diesel cycle, which was a closed system analysis. Okay. So any questions? Otherwise, I ended up using all the time. I didn't get to the solutions. Hopefully next class. If not, I'll just make a recording and go over the solutions because I don't want it to waste on example time.
Good question, Professor.
Mm-hmm.
For the closed feed water system,
Yep.
how does the mass flow rate work there? Is it just consistent up until the mixing chamber? Is that
So it's the same
that big
idea
of
as the open. So this has y here, and this has 1 minus y. Because we're splitting this mass of 1, the total mass here. And we're splitting it here, right? So then y amount flows all the way, yeah, like all the way here until you get to the mixing chambers. That's all the y amount, right? 1 minus y flows all the way through here to the mixing chamber, and the mixing chamber combines the two, and we get back to the full amount, or 1 amount, right? Right there. Does that answer your question?
yeah.
Okay. Other questions? All right. Otherwise, that's it for today, and we'll do examples next class.